For establishing, maintaining, and clearing a connection, signaling information must be exchanged between the end user and network devices. So the signaling process enables the network to manage communication sessions effectively from the moment a call or connection is initiated to its termination. In traditional fixed line networks, analog telephones signaled their connection requests in a straightforward way. When the receiver was lifted off the hook, it indicated to the network that a connection was being requested, and the phone number was sent to the network through one of two methods. Pulse dialing, this involved the phone sending a series of electrical pulses corresponding to the dialed numbers. Each digit was represented by a specific number of pulses. And dual tone multi-frequency, DTMF dialing, also known as tone dialing. This method used a combination of two tone frequencies to represent each number. So it was faster and more reliable than pulse dialing. With the advent of fixed line ISDN phones and GSM mobile phones, signaling evolved significantly. So instead of relying on the same physical channel for both signaling and voice, modern systems use a dedicated signaling channel for exchanging control information. For example, information such as the destination phone number and call setup parameters are sent as digital messages through this dedicated channel, enabling faster and more efficient communication. The SS7 protocol is also integral to GSM networks and has been enhanced by the European Telecommunications Standards Institute (ATSI) to address the unique needs of mobile communication, such as subscriber mobility management, tracking and updating a subscriber's location as they move. The SS7 standard defines three primary types of network nodes that perform distinct roles. Service switching points, SSPs. SSPs are switching centers, also referred to as network elements, that handle the setup, transport, and forwarding of voice and data connections. These are responsible for initiating and terminating calls and managing the signaling required for these tasks. Service control points, SCPs. SCPs are specialized databases equipped with application software to influence the connection process. For example, in GSM networks, SCPs store the current location of a subscriber. During a call setup to a mobile user, the switching center queries the SCP to determine the subscriber's current location to forward the call accordingly. And this functionality is crucial for mobile communication and is detailed further in next sections of our course. Signaling transfer points, STPs. STPs serve as intermediates that forward signaling messages between SSPs and SCPs. Not all nodes in network are directly linked, so STPs ensure messages reach their destinations efficiently, functioning similarly to IP routers in the internet. However, unlike IP routers that handle all types of packets, STPs only forward signaling messages necessary for establishing, maintaining, and clearing calls. But the actual voice and data are carried on separate dedicated links between SSPs. The general structure of an SS7 network includes STPs, SCP databases, and SSP switching centers interconnected to enable seamless signaling and communication. The arrangement ensures that signaling messages traverse the network efficiently, even when the multiple nodes are involved. While SS7 was initially designed for circuit switch networks where a dedicated path is established for the duration of a call, it has also been adopted for virtual circuit switch networks, such as those operating over IP. In IP-based networks, signaling messages are no longer confined to dedicated time slots on an A1 link. Instead, they are encapsulated within IP packets and transmitted across the network. The adaptation allows SS7 to function in modern communication infrastructures, bridging the gap between traditional telecommunication networks and newer IP-based systems. But don't worry, in this lecture and also next lectures of our course, We will explore the SS7 protocol stack in greater detail, and we will discuss how SS7 messages are transported over IP networks, illustrating the protocol's versatility and continued relevance in evolving communication systems. So, the key takeaways from these informations is SS7 enables seamless communication by managing signaling between various network nodes. It has evolved from analog pulse and signaling to a sophisticated protocol capable of handling modern telecommunication demands, including mobile subscriber mobility. The SS7 protocol stack supports both traditional circuit switch networks and modern IP-based systems, showcasing its adaptability. The signaling system number 7 is a set of telecommunication protocols that plays a critical role in managing and controlling telecommunication networks. To understand SS7 better, we can use the well-known Open System Interconnection USI 7-layer model as a reference. The USI model provides a standard framework for describing communication protocols across different layers, which you can see in this illustration, alongside the SS7 and TCP/IP protocol stacks. And at the very foundation of the stack is MTP1, which is Message Transfer Part 1, which corresponds to the physical layer in the USI model. So this layer defines physical properties of the transition medium, such as type of cables like copper, fiber optics, and so etc., signal levels, electrical or optical, and transmission speeds measured in bits per second. For example, imagine you are setting up telecommunication network. The physical layer ensures that the infrastructure, like the type of cables and signal properties, meets the requirements for reliable data transmission. And moving up, the data link layer is implemented by the MTP, Message Transfer Part 2, and its primary role is to manage the framing of data into packets and ensure proper synchronization between sender and receiver. Key responsibilities include framing messages into packets. This includes marking the start and end of each packet, error detection and correction. This ensures that the error introduced during transmissions are identified and corrected when possible. So you can think of this layer as a traffic officer ensuring that all vehicles, which is data packets, have proper identification and follow their assigned routes without collision. The network layer is represented by the MTP3, Message Transfer Part 3. This layer handles the crucial task of packet routing, ensuring the data reaches its intended destination. So functions of MTP3 include assigning source and destination addresses to packets and forwarding packets across different network nodes. Instead of IP addresses as used in TCP/IP, MTP3 utilizes point codes to identify network nodes. These point codes serve the same purpose but are specific to the SS7 system. For example, when a call or message is transmitted, MTP3 protocol ensures it is routed to the correct telephone exchange or service. From layer 4 to 7 of the OSI model support a variety of SS7 protocols depending on the application. And here's an overview. ISUP, Integrated Services Digital Network User Part. So the ISUP protocol is used to manage call setup, control, and teardown. For instance, when a mobile subscriber, for example, party A, initiates a call to a fixed line subscriber, let's call it party B, ISUP facilitates the exchange of messages required to establish the call, alert the recipient, maintain the connection during the conversation, tear down the connection when the call ends. Now you can see the example call flow in this illustration. Party A dials party B's number. The mobile switching center of party A analyzes the dialed number and detects that it belongs to a fixed line network. Then call is forwarded. If the mobile switching center and fixed line switch are directly connected, the call can be routed directly. Otherwise, intermediate nodes such as signaling transfer points, STPs, handle the routing. The mobile switching center sends an initial address message IM to the fixed line switch, indicating the call number and desired channel. Then the fixed line switch sends an address complete message ACM back to the mobile switching center to confirm that party B is being alerted. Then conversation begins. When party B answers, the fixed line switch sends an answer message ANM to the mobile switching center, enabling the conversation. When either party hangs up, a release REL message is sent, followed by release complete confirmation. Signaling connection and control part. SCCP operates on layer 4 and serves a function similar to TCP UDP in the IP world. It manages application identification and routing of non-circuit related signaling. So, by application identification, I mean it differentiates between applications running on the same node using subsystem numbers, SSNs, instead of port numbers. And routing of non-circuit related signaling, which is essential for database access and messaging services. For example, just as TCP uses port 80 for HTTP and port 21 for FTP, SSCP uses unique SSNs to route incoming messages to applications like billing systems or voicemail services. Transaction Capabilities Application Part, TCAP, is used for querying databases in telecommunication networks. It standardizes how messages are structured and exchanged to retrieve information such as subscriber location for call routing, like via home location register, HLR, and service-specific data for applications like roaming or billing. An example use case is when you are roaming internationally. TCAP enables the system to verify your subscription details and ensure seamless connectivity. While SS7 is specifically designed for telecommunication networks, parallels can be drawn with the TCP/IP stack, which is commonly used for internet communications. MTP3 in SS7 is similar to IP in TCP/IP in routing packets, and SCCP in SS7 is very similar to TCP/UDP in TCP/IP in managing sessions and applications. And this comparison helps bridge the gap for students familiar with IP networks, making SS7 concepts more relatable. And that's it with our lecture. The SS7 protocol stack is the backbone of traditional telecommunication networks, enabling reliable signaling for calls, messaging, and database queries. So understanding how its layers correspond to the OSI model provides valuable insight into the architecture of telecommunication systems and prepares students for exploring more advanced topics like signaling security and modern IP-based telecommunication systems. I'm Typhoon, and I'm waiting you in next lecture. Thank you for watching.